my question is.
Yeah, go ahead.
Okay, my question is that why is it given the same code, but when we run it on different machines, we get different accuracies? Like yours was 70%, mine was 65%. Could it be the okay? What could be the reason for that?
Question. Come on, guys. I've answered this question before. Who can answer it?
Okay, I can say what I still remember. You talked about kuchukucha makadzi. So one and every person can chukucha very different.
Probability.
That is absolutely correct. It's got to do with the kuchukucha question, so that it was, the results will be slightly different. Slightly, just yeah. But I can show you how to achieve the same results.
Exactly.
Right? I can show you how to achieve the same results.
Yes, I would be grateful for that.
Yeah, I'll show you how you achieve the same result. No problem. So what we'll do for now, so we can actually do it in this exercise. Can you? So, well, what I will do. So what I will do is, so the person who comes up with the best results in your class, what I'll do is I'll pay for their certification year TensorFlow. I think it's worth about $400, right? So when I enter the best results, I'll pay for their certification. Yeah.
Yes. Interesting.
Please come again.
Yes, Doc.
Yeah. So the person another. I think it's $100. It's $100. So the first 5 results, the best 5 results, they knock by the other for your certification. In TensorFlow, right? So you can write your TensorFlow. I'll pay for it personally.
Doc, the first 5, you mean in terms of accuracy?
The first 5 combined result exam in my projects, group project and individual project.
The top 5, Michael.
So who's joining me?
Thanks, Doc. Garai mandipa Mariage.
In the number 1.
Yeah, so my results, I'm not, so we'll then sort those out. Yeah. So now, what I need you guys to do, can you please?
Hi, Doc.
Yes.
Nyaya matoro yakanaka ingade mangoti ndo anobhambo yaomboita 1 year intern kudeep analytics uko kachinyatsofunda chezvo.
That can be arranged. In fact, what I'll do is, Aneta number 1, I'll give them a job to CBZ as a data analyst. Guaranteed.
ade mangoti 5 kuti
Six are high.
Can I do
Five
a
is five is not possible.
classification? Can I do
Five is
one
not
lady,
possible.
one male?
Yeah,
Five
no
is
person to balance.
5 is not possible because of obviously. Otherwise, those are accused of the punishment that which. Yeah, but now okay, number one, first lady, and number one male, number one female. Let's make it that way.
Okay.
Apa balance apa dogo mango ma senior mango ma junior patroni handicap.
No, not to balance the same. Because in India, you cannot go do it by age. Huh? But I am a senior citizen. I am a youth.
Open boys apa.
I think Jogu, you are quite fair enough to say one female, one male. So it's now on our part to prove ourselves.
Yeah, so it's not part to prove yourselves. Right? It's not in my hands. What I need you to do for now is download this Jupyter notebook. So this Jupyter notebook uses the same data set, all right, that the my dogs and cats. So just put it in the same folder. So can you please download this and then I'll start transfer learning. I just need 5 minutes. I've got the best water pipe plumber out here. So just give me 5 minutes. But for now, just download the notes and the notebook.
Sorry guys. My data says is it 213 megabytes or in router za compress out item madiki before I download.
It's correct. It's a big document.
All right, thanks.
Hi guys, so you managed to download?
Yes, Doc.
Okay, all right. So let's start. Transfer learning. A quick one. You can see my screen, yes?
Yes, Doc.
Right. So we're going to look at the origins of transfer learning, and then we're going to look at CNN architectures and transfer. What you mean by transfer learning, right? So the origins of transfer learning comes from the largest image classification challenge on the planet. So this image classification challenge has got over 100 billion images with over 1,000 classes. So the competition is held every year with all the big companies in AI competing. So you've got Google, Facebook, Uber, and all the big universities like Oxford, Harvard, and so on. So the largest AI competition is the largest AI competition in the world, and companies compete in reducing the error rate or accuracy of the classification. So companies compete in coming up with the best hyperparameter tuning for convolutional neural network architectures. They come up with different combinations of neural network architectures, right? So these are the origins of transfer learning. It comes from the ImageNet challenge, right? So so let's say, for example, in 2010, the error rate was 28.22%. That was reduced to 25.8%. But these two were used in shallow networks. Then there was a big jump from 25.8 to 16.4 when they started using deep neural networks with 8 layers. And you can see this other one, it was used in shallow networks. Then the next one was another one with 8 layers, but they reduced it to, but with more neural networks, they reduced it to 11.7%. And then I believe this is in 2016, the VGG stands for Oxford Visual Graphics Group. They increased the number of layers to 19 layers, and they reduced it to 7.3%. And then it went on to 22 layers and so on and so on. And then Google created the architecture called GoogleNet, which reduced it to 6.7% in terms of the error rate. And then Microsoft created what they called ResNet, which reduced it to 3.57%. And then now, I think the winner is actually Facebook, which reduced it to almost 0.1%, right? So what these companies do, basically, they create architectures of these convolutional neural networks. And these convolutional neural networks take up to 10 months to train, right? 10 months to train on infrastructure that costs hundreds of millions of dollars. Right? So then the idea is, instead of you coming up with a new architecture, what you do is you look at who created the best architecture. You copy that architecture, right? and then you utilize that architecture for your own classification for convolutional neural network, because you will never have, right, the same type of infrastructure to be able to train your network and do hyperparameter tuning for a whole 10 months, right, to come up with the best combination of hyperparameters for the best optimized model. And so if you look at, for example, Google with their different types of architectures, they've spent over $100 million creating this type of architecture, even though the price might be $10 million, right? Might be much less than the cost of training the models. So the first one was created by University was created by Jeffrey Hinton and Alex Skrisheny, or can't pronounce his Russian names. So the two of them created an architecture that they called LeNet. So it was a 7-layer convolutional neural network, which was, and this 7-layer convolutional neural network is what then became the standard for optical character recognition for handwritten digits. So when you see in the olden days, they used to have check processing systems that used to convert the text written on checks to typed text, right? So it would used to convert handwritten digits to text. So that used the LeNet algorithm, right? So the guy who actually developed, the team that actually developed it is actually the same team which is heading the Facebook AI team, right? So they are the ones who developed the LeNet architecture. So the LeNet architecture reduced the accuracy rate from 28.8% to 16.5%, which was a big jump, right? And then so this is the architecture for Alex. So this was so the first one was LeNet, which was created by LeCun and Alex, and then this is the same team that then created one called AlexNet. So this one was created by Jeffrey Hinton, Alex Krzyzewski, and LeCun. And they're the ones who collected AlexNet. So AlexNet comprised of 5 convolutional layers and 3 fully connected layers. So these 8 layers combined the 2 new concepts at that time. So they're the ones who started with the concept of max pooling and nonlinearity, right? Using a rectified linear unit as the activation function, right? And so in 2012, Hinton's deep neural network reduced the top 5 so it reduced the error rate from 26% to 15%, the biggest achievement ever in 5 years, right? So the network was very similar to LeNet since it's the same team that created it, right? And it was a much deeper neural network, and it around 60 million parameters. And then so the runner-up of the 2014 ImageNet Challenge is called Oxford University Visual Graphics Group, short for VGG. So they called it VGGNet. So what they did with VGGNet is they had an input layer, and what they did is they created a repetition of 2 convolution layers and max pooling, 2 convolution layers, max pooling, 2 convolution layers, max pooling, 2 convolution layers, max pooling, and so on, right? So that's the architecture that they created, which they called VGGNet. So this one then was run up in 2014 in the ImageNet challenge. So each convolution layer had a kernel, had a filter or kernel size of 3 by 3 and a stretch of 1, and where the padding was the same, and the max pooling layers were configured with a window size of 2 by 2 and then a stride of 2 instead of stride of 1 by 1. Thus, they halved the size of the image at every pooling layer. Right? And then the winner for 2014 was Google. So Google created what they call the Inception or GoogleNet, the Inception version 1, right? This architecture reduced the error rate to 6.67%, right? So this architecture was composed of concatenating average pooling with convolution layers, as shown like this. So they would concatenate pooling and convolution layers, right? And what they would do is they would then add some regularization. By regularization, we mean they would reduce the number of neurons that are used at some of the layers to make sure that the model does not overfit. Right. So then Google then created in 2014 they created Inception V1. Then they improved the model, created Inception V2. Then they further improved the model in 2016 called Inception V3, and then in 2017 they created Inception V4, and in 2019 they created Inception V5, which are further improvements of the initial Inception V1 models. Right, and then Microsoft in 2015, ImageNet competition, they reduced the error rate to 3.57%, which is lower than human, right? So what that simply means is they managed to, if you compare the best performing human in terms of classifying images, and you compare it with the convolutional neural network architecture that was created by Microsoft, called residual network, or ResNet for short, it was actually performed much better than any human being could do it. Right. So with Microsoft, they introduced a new concept in convolutional neural networks, what they call skip connections. Right. So what that simply means is if you have so let me go to the whiteboard. Right. So sure. So what that simply means is if you've got a layer 1, a layer 2, and if you've got layer 3, layer 1 connects to layer 2, and layer 2 connects to layer 3. Then you also have a connection from layer 1 that connects to layer 3 and skips layer 2. And then you then also have, if you've got layer 4, so layer 2 will also be connected, will skip layer 3 and be connected to a layer 4. So they call them skip connections. Right. Right. So what that simply means is when you are creating these skip connections, well, what that means is you are now feeding whatever information that you're feeding from the layer that you have skipped is being aggregated in also in the next layer. So you're actually creating a combination uh, um, of information from the two different layers, right? By skipping information from one layer and feeding it into the next layer. So it was just a concept that Microsoft was playing around with. So with this architecture, Microsoft then won the competition in 2015. Right. So one thing you realize about these different architectures, they're extremely compute resource intensive, right? And they use a lot of hyperparameter tuning, right? And architecture, or what we call architecture search. We'll explain what that means, right? So you then realize that you don't have the infrastructure to do proper hyperparameter tuning. Right? If Google's hyperparameter tuning takes 10 months on billions of dollars worth of infrastructure, what about your infrastructure, right? Which is not even worth a couple of thousands of dollars. So hyperparameter tuning is not practical if you don't have the compute infrastructure. Right? So what are the options for creating high-performing models that yield the best results? So hyperparameter tuning is notorious for running for months because you want to be able to exhaustively search a parameter space of millions of parameters to come up with the best performing model. So therefore, the trick is to copy what these architectures have done and apply it to your model, right? Is to just copy, right? That's the whole idea, right? So the idea is if you try your own hyperparameter tuning, it will take a very long time. So therefore, you take existing architectures that have been proven to be able to achieve very high results, right? And you use those architectures, right? So what is transfer learning? So transfer learning is the application of skills, knowledge, or attitudes that were learned in one situation to another learning situation, right? So normally in those situations, you are learning from someone who had vast amounts of data, right? So in the image challenge, they had 100 billion images, right? 100 billion images are going to take a very long time for you to try and even collect. They will probably not even fit on your machines. So you draw the learning curve to understand whether your data is sufficient. So one thing you realize is when you have insufficient data, your model accuracy will plateau. But when you add more data, the performance of the algorithm. One second, the plumber is making too much noise.
Hi guys, is it me or we lost Doc for a minute?
No, he actually requested to be
He
excused a little bit.
excused himself.
Oh,
He excused himself.
Guys, when I will record the lecture, please. Just wanted to know.
Ishmael ndo anoswanza kutibatsira about this.
No, Tinashe Marume.
What about the right?
Okay, Tinashe, okay.
Because the last three and nakuona paakazomakanda. I just wanted to know kuti ari record.
On his YouTube page.
I just saw one.
No, unaenda pakanzi videos and then it will show you everything.
Oh, so for the the videos from the 18th, like I can't see Wednesday, Thursday, Friday, na joke.
Yeah, he has been posting them.
Aribo.
They're there. Even your names.
No, thanks so much.
Okay.
Oh. No, thanks so much.
All right. Yeah. So basically, the idea with transfer learning is you're taking experience from a very high performing model and injecting it into a model that you will then purpose for your own task, right? So improving a learning task via incorporating knowledge from learning tasks in other domains. So with different feature space and data and data distribution, right? So basically what you're doing with transfer learning is you are taking an existing architecture which has been trained on a particular domain, and then you refashion it for your particular purpose. Right, and then you then retrain it with new data, even if the data set could be small, right? So let's say, for example, we've got from the ImageNet challenge, we use one of the architectures. We then fine tune it with our own data, and then we train that neural network that we fine tuned with our own data, and it will still perform very well, right? So the way it will work is let me go to explain. So let's say, for example, you've got let's take, for example, a ResNet, right, or residual network by Microsoft, right? So this one was trained on 1,000 image classes. in 100 billion images, right? And then you've got your own simple problem, right, of classifying a dog and a cat, right? So in this instance, you've got two classes, and this one has got 1,000 classes, and it's got 100 billion images. And you probably have, in our instance, with about 8,000 images. So what you do is, if we look at the ResNet architecture, for example, if we look at the ResNet architecture, for example, so what we then do is, let's take this architecture and put it to so what we do is we simply do one thing. We change input parameters, right? Change input parameters so that it matches my situation, right? Right. So in this instance, it's 1,000. So it means I change the input to match my situation to be able to deal with two images, right? And then also the output is designed for 1,000 classes, and then change the output for two classes, right? And then I keep everything the same, right? So what I do is I keep all of these things the same. I change the number of the output, which is the number of classes in this instance for ImageNet is 1,000. I change that to 2. And I also change the input, right, which is 100 billion images to be able to deal with 8,000 images. So those are the only changes that you need to make. And then what you then do is the new architecture that you've tweaked, you retrain it. You retrain it, and it will perform just as well as the original architecture. Right. Yeah, is this clear? Come on, guys, is this clear?
It's clear, Doc.
Yes, Doc.
All right. Right. So this is an example of the pre-trained model. So pre-trained model, right? So this is the old classifier. You then add your own new classifier, right? By changing the fully connected layer to specify the architecture that you want for your problem that you try to solve. And then you also change the input, and then you freeze everything else. Right? And then what you then realize is with transfer learning, it starts off with a very high accuracy, and then it will perform better and better than starting from scratch with your own architecture, which will start from 0. And then as it tries to improve its performance, with training, it will never reach the same type of performance as the one with transfer learning. Right? Okay, so that's transfer learning. That's easy enough to understand. Yes. So I'll show you how it works. So if you've downloaded the where's the okay. Right. So in this instance, if you look, we are going to import ResNet, right? Right. In this instance, we're going to import ResNet, the residual network from Microsoft, right? So everything else here you understand, right? And you remember the scaling, right? Yes. So what I'm doing is I'm now applying transfer learning to the dogs and cats problem, right? So I'll do exactly the same, right? Import my data, right? I've got 8,000 images belonging to 2 classes. Then I need to be able to validate the model. And what I now do is my base model, right, is ResNet, residual network from Microsoft, right? Then I'm importing its parameters from ImageNet, right? So what I want to do is, if I show you from here, so what we are calling the top part is equal to 4 simply means this is our output layer, which is the top part. We are changing this so that we've got 2 classes instead of 1,000 classes. Therefore, we want to tweak it so that when we're importing it, we're saying that we want that fully connected layer to be false instead of having 1,000 classes. We want 2 classes, and then the input shape still remains the same, 64 by 64 with three channels. You understand what that means? It means red, green, and blue. Right? So we import our base model. So what you realize is it will start downloading this model from the internet, from Microsoft. And then if I then get the summary, you will see that now summary of the model, my input now is 64 by 64, and then everything else is still the ResNet architecture. But what is now changed, the output layer now has 2 classes instead of 1,000 classes, right? Yeah. So what I then do is we've removed this part. We've removed the top, the fully connected layer. So what that simply means is now we now need to add our own fully connected layer. So I now create a sequential model, which I then add my base model from above. Then I flatten it, still the same process. Then I now change my output to say I now have 0 or 1, and the activation function is sigmoid as opposed to a softmax with 1,000 classes. Now I've got 1, I've got 0, 1, which are 2 classes, right? And then I can then have a summary of my model. You then now see it's got 2 classes as the output, with 23 million parameters, right? So, and then same, I compare my model, right? I now use binary cross entropy, right? And then I then train my, I use 10 as the number of epochs to train my my model, right? And then you'll see when it starts, it will start off with a very, can you see? It starts off with a very high. Start off with a very high accuracy, and it will always end with something extremely high. So this model will give you, for any type of dog or cat that you give it, it will most definitely, even if it's wearing a mask, it will most definitely identify it. Are there any questions so far, guys? Right. So for those of you who like music, so you can think of it in this way, right? So this is what these current young music guys do. So you take you take the bass and drums, right, from a popular song, from a popular old school song, right? Old school classic. You add your own other instruments and voice, right? And then this becomes the new sound. Right? So this is what a lot of these R&B R&B rap and Zim dancehall, right? EGC, that's how they produce their music, isn't it? The beat is not original, isn't it? Come on, guys.
Yes.
Yeah.
Yeah, the beat is not original, right?
Yes.
Right? The beat is
Yes,
not original, so they take some bass and drum from some existing popular song. They then filter that and add their own other instruments and voice, and then that becomes a new sound or song that they release. Yeah, so this is exactly the same concept of transfer learning, right? So you're now yes. Sorry.
Oh, so I was saying, thank you, Doc. It's now well simplified.
Yeah, it's exactly the same, right? Because you notice my songs Zim dance Vakaba from Beanie Man, Vakaba from Peter Tosh, or all those old songs, and then they add this and that to make it look like it's new, but it's not really, right? And then they add their voice to it. And then you guys make them to tamba mchitenga right? So you can see in the first instance, the accuracy is 70% on the first epoch, right? Of which, if you recall, on the other model that we created on our own for dogs and cats, after 5 epochs, that's when we go to somewhere around 70%. But this one, on the first epoch, we are at 70%, right? songs and then they combine to mix it into their own song, right? So this is an example of transfer learning. You know, this song was very successful, so there's no need to create your own new beat. You're using proven success to make sure that you succeed. Yeah, so that's making sense. Yeah, probably that's an easy example to understand, because a lot of you are able to relate to this business of cannibalizing from old songs to create new songs. Yes, guys.
Yes, Doc.
Yes, Doc.
Yes, Doc.
Yeah, then you discover it's exactly the same thing that we've done. The only difference is you can see the model accuracy is much higher than what we achieved with our own model that we came up with from scratch. So transfer learning applies to convolutional neural networks. It also applies to natural language processing, where you have trained a model, for example, to understand a language, and you want to extend it to be able to add other languages. We'll see how that is applied in natural language processing. Any question, guys? So you now understand what transfer learning is, isn't it? Very simple to understand.
Yes, Doc.
And another good example is you have another good example is you have a Muskana, right? Yes. So Muskana anengane tuvudzi twake tudiki so, right? Then overtenga Brazilian weave, over increase beauty accuracy yake much. From 30% to 80%.
The level of violence in this.
It transfer learning here.
Let's clarify. This might not end well.
I hadn't like this. Fortunately, I know all Nigerians, but hey, yeah.
That's a good example as well.
Doc, let's say ndashingira mzama ndatsavatsa ndogona kupere tuma examples.
No, these are good examples, right? 1-year music that really applies, right?
Yeah.
Right. So yeah, it's the same thing, right? Because when anotora weave, right? Anotora weave, right? Zikanonzi yakanaka ibvudzi rakanaka, right? Waikombina nemufushwa wake, right? Wakombina nemufushwa, right? Anenge anati mufushwa kuno, and then the result.
But mfushwa wakanaka wani.
Yeah, that's not one more fun, boy.
It's transfer learning. increase our beauty accuracy, right? From 30% to 80%. And this was it was transfer learning here.
Kwasara my eyelashes.
This was what? Netuma eyelashes, Netuma eyeshadow dresses.
The beauty filter.
That is beauty accuracy increase, right?
The foundation.
The foundation that very to increase, right? From 30% to 80%.
99. And it's not a shanda because most of you look.
So therefore you never forget transfer learning, right? Let's see how well this thing is performing. Right, so you can see the accuracy here is improving and so on, right? So you get the idea, right? So you can also run the model for yourselves, guys, right? So now you understand transfer learning, what it's all about. You're using existing architectures that have been proven to work very well, and then you cannibalize those to fit your own situation. Same thing with my weaves and music and so on. It's exactly the same concept. Yeah, guys. So
Yeah,
so
just
please,
a question, Doc.
yes.
Since you have highlighted that ResNet, these are architectures that are used in CNN, that is convolutional neural networks. Are there other already existing architectures for either deep learning or some other?
Yeah. So remember,
neural networks?
CNN is a deep learning architecture, right? Specifically for computer vision, right?
Yes.
Then you also have transfer learning that applies to natural language processing, right? NLP, right? So you can take an existing architecture that has been trained on a specific language, right? And then you can then use that for your own language.
Yeah, maybe to follow up on that, may you kindly share, for example, already existing architectures for NLP, or maybe somewhere that we can get them.
Yeah, so there's an architecture by Google called BERT. Right. We'll talk about BERT when we're doing a recurrent when we do a recurrent neural networks. Right. We'll talk about this when we do a recurrent neural networks. Because mainly for natural language processing, you use recurrent neural networks. So if I come here and I search for Google. Right. And you find that Google have created their own architecture called BERT, which is used for natural language processing. Right. It improves greatly any type of language processing. Right. Whether it's classification, whether it's search, it's query, or whatever it is. So you can actually see, let's see what you've got. Right. So this is what the Google BERT model looks like. So we'll talk about it more when we're actually doing. Right. So this is an example actually of. right? You can take an existing model, right, which has been pre-trained by Google. Then you can fine tune it for your own situation. So therefore, you can just create your own model, which is very good for natural language processing, just as much as. So what I'll show you some of the stuff that I did. What I did is I took a Shona Bible, right? I wanted to see because with natural language processing, we can create an algorithm that can generate a language. So I wanted to see if we can understand the Bible and generate its own verses that actually make sense. So then I took a Shona Bible and then I fed it into a model that was pre-trained, and then I just tweaked it a little bit, and then it started learning Shona Bible verses, and then I asked it to then start generating its own verses. So you'll be surprised some of the verses that it was generating are extremely accurate from a biblical point of view, right? Yeah, so yeah, I'll show you an example of that when we're doing a recurrent neural networks. So let's check how well this model is performing. So it's still training, but anyway, you get the you get the idea that you're not starting from scratch. You're using an existing model, and then that model allows you to use existing knowledge already, which we know works very well to our own use case. All right, guys. So that's transfer learning, simple and straightforward. So you'll realize if we image. Let's see, who's the current ImageNet champion? ImageNet champion. This one is talking about this old architecture. Doesn't tell us who. Very short paper. It doesn't tell us who the current champion is, because I think I've lost track. So see 2017 news. Oops. Broken link. So you see, it's exactly the so it's all based on this challenge. So it's called ImageNet Large Scale Visual Recognition Challenge, ILSVRC. So you can also compete if you want to compete, but if you don't have the infrastructure, it's pointless. You can actually download the data sets and so on. You see, it's got over 1 billion. It's got 1,000 classes. Yeah, but that would take forever to run on your machines. Yeah. So so there we go. We've got our model that that is still training, but that will take a bit of time because it's a very huge model. So what I would encourage you guys to do is you don't have to follow what I've done here, for example. What you can do after you flatten is you can add another layer. You can actually say model dot add dense. Let's say let me say 100 activation is equal to value. Yeah, you can also add other layers like that after flattening, because then this is your fully connected layer. I went straight to this. This is probably why I'm not getting a very high accurate results, because I went straight from the flattening to the output. I should have probably added some more hidden layers. Model dot add a dense let me stop this. Okay, you can see I've created this model, and this should perform better than the previous model. Yeah. So the idea is you can tweak it to now do whatever you want it to do using a base model from ResNet. All right, guys. So if there aren't any more questions, the best is to try it for yourself, right? So I think that's it with a transfer learning.
Excuse me, Doc.
Yes.
You said you show us how to have the same output.
So sorry, you're breaking up. You're saying?
Okay, the other time I had asked why our accuracy outputs are different, and you said you might show us how to have the same output.
Come on, what is this thing? All right. Yeah. All right. So, can you hear me?
Yes, Doc.
Yes, Doc.
Yes, Doc.
All right. So, right. So, if you want it to be exactly the same, right? You say from numpy.random input seed, right? And then what you then say is you want to restrict the extent of the randomness. Let's say we want to say 100. Right? So if I say seed 100, right, what that means is the way we generate, the way we are going to split our training and our test set and choose it randomly, it will be more predictable, right? Because we are seeding that randomness, or we're controlling that randomness. So with this, it will always give you the results which are exactly the same. So that's how you control randomness, so that you get exactly the same results. Yeah? Does that answer your question? So try it.
So I just leave it as seed 100, and the model automatically.
Yeah, absolutely. It will then control the randomness. try to see you all get exactly the same results. Exactly the same. Or you are creating your own original model.
Yeah, pakaipa.
Yeah, pakaipa for sure. All right, guys. So what we'll do is we also continue after your exam so that we give you time to read. Okay. So after exam, we'll also continue. Yes, guys. So after your exam.
Thank you, Doc.
All right, thank you. So just revise that paper and area, and I gave you examples on how to answer those things. So that should help a lot.
Okay, thank you.
All right, guys. All the best for your exams.
Thank you, Doc.
All right. Bye-bye.